We're in chapter 26, Working Problems, for Classical Physics 2. And the first problem we're going to work is number 4. What is the internal resistance of a 12-volt battery, car battery, whose terminal voltage drops to 8.4 volts when I'm drawing 95 amps? And then we want to know what is the starting resistance of the starter. Okay, so we're going to look at figure 26.2. And I'm between two pages and I can't find 26.2. Okay, so there's 26.2. And okay, I finally found page 26.2. Okay, so I've got some battery. That's a 12-volt battery. And I've got some internal resistance R. And I've got the terminals of the battery. And then I've got some starting resistor, big R. And I know that, okay, so those are the things I know. Alright, so, and I've got a point A and I got a point B on my battery where I hook up the terminals. Okay, so the voltage A to B has to be whatever the voltage of the battery is minus the current going through it times the internal resistance. Okay, so we know the voltage A to B, 8.4 volts. We know it's a 12-volt battery, and we know the current's 95 amps, and we want to know what little r is. Okay, so, and that little r isn't that apparent to be a little r, but that's okay. Little r, I put these guys on the other side of the equation. So 8.4 minus 12 divided by minus 95, and volts on top, amps on the bottom. And my answer is in ohms. I put in my calculator 0.038 ohms is the internal resistance of the battery. So that's the A answer. And then I ask myself, what is the B answer? Well, voltage A to B has to equal IR. Okay, so big R has to be that 8.4 volts, which is the terminal voltage, divided by 95 amps, and that gives me a starting resistance current of 0.088 ohms. And that would be pretty good, because what is your starting here? Starting guy is just a hunk of wire, and it's not going to be much resistance there. Okay, moving on to number 16. Oh, turning the page when I shouldn't be. No, I should be. Number 16. Determine the equivalent resistance of the circuit shown below and the voltage across each resistor. Okay, so I've got I'm going to draw the picture a little differently than they have it. So I've got a battery that's 12 volts. And then I've got a resistor that's 960 ohms. And then I've got two other resistors that are 820 and 680 ohms. If I could spell 680 ohms. Okay, so this is going to be a circuit that is equivalent to 12 volts and 1 resistor, resistance total. And the resistance total is going to be the 960 ohm guy plus the 820 ohm guy in parallel with the 680 ohm guy. Okay, so that's the math we have to do. So that's going to be 960 plus 1 over 820 plus 1 over 680. Because in parallel, the 1 over parallel circuit, 1 over R total would be 1 over R1 plus 1 over R2, and therefore we have 1 over 1 over. Okay, well, anyway, in any event, the equivalent resistance, also known as the total resistance, 1331.7 ohms, but we only have 2 significant digits, so we'd probably round that off and call it something different, and 1300 ohms would probably be good enough. Well, it would be good enough because we only have 2 significant digits. The B part of the answer, we want to know the voltage across each of the elements. Okay, so here we would find the total current. Well, the total current would be the voltage across the, divided by that equivalent resistance. So I've got 12 volts. I'm not going to divide by 1300 though. I'm going to divide by 1331.7. That's only my final answer that I keep significant digits. And I'm going to come up with 9.01 milliamps as my total current. Well, that 9.01 milliamps, all of it has to flow through the 960 ohm resistor. So the voltage across the 960 ohm resistor has to be 9.01 milliamps times 960 ohms, and that'd be 8.6 volts. Well, Kirchhoff's law says the voltage, the summation of the voltages around a loop has to be 0. So if I start with 12 and I go down 8.6, the rest of it has to be across the parallel circuit. So that means the voltage across the 680 ohm resistor, which has to equal the voltage across the 820 ohm resistor because they're in parallel, is going to be 12 minus 8.6 volts, which is 3.4 volts. Okay, number 18. What do I have? Isn't that lovely? I have a lot of R's. Determine the equivalent resistance of the latter of equal resistances, 120 ohms each, blah, 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 okay. What is the current through each of the 3 resistors on the left if we hook up if we hook up a 50 volt battery is connected A to B? Okay. Alright, so I've got A, and I have B, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and they're all R. they're all 122, 125, but we're just going we're having a problem, a technical problem. What happens is that the software that I'm using at the end of 10 minutes will turn off, and then I have to restart it. And after I do that, it can run for hours and hours and hours. It's a Microsoft thingy. Alright, so we're back to our diagram. Alright, so I look at this and I say, well, the equivalent resistance, well, I'm going to have those three R's in parallel with that R there. Okay, so they're going to be in parallel with that R there. And then they're going to be in series. That group is going to be in series with those two R's. So we're going to go plus 2R. And then that circuit's going to be in parallel with this 1R. So that's going to be in parallel with 1R. And then that whole thing is going to be in series with 2 more R's. Okay, so I've got 3R in parallel with an R, and then I got 2 R's in series with that combination. I've got 1 R in parallel with that combination, and then I have 2 R's in series with that. Okay, so that's how I'm going to write it. So now we got to do the math. Okay, so the equivalent resistance, if I could spell either equivalent or resistance. Oh, that's really bad. Much better. Okay, so I'm going to have 1 over 3R plus 1 over R plus 2R in parallel with R plus 2R. Okay, well, 1/3 plus 1 would be 4/3 R, 4/3 over R. That would be inverted to 3/4 R. So 3/4 R plus 2R would be 2.75 R in parallel with R plus 2R. Okay, well, now that I stuck that one in, I got 1 over 2.75 R plus 1 over R plus 2R left over. And so I guess I can't do that one in my head. I'll probably have to do something like take out my calculator. So the R is going to be on top when I get done. Alright, so I've got 1 divided by 2.75 plus 1 equals, and then I want to go 1 divided by the answer. Okay, so I'm going to end up with 2.73 repeating R. And I'm going to use my handy calculator and say if I had 2.3 repeating and I changed it to a fraction, I would end up with 41/15 R. Okay, so the A part of the question wanted to know what the equivalence is if the equivalent resistance is total resistance if the R's are all 125 ohms. So I do that math real quick, and I end up with, we'll round it off to 342 ohms is the that resistance. Okay, so the B part of the answer wants to know what is the current through each resistor on the left. Okay, so what we have, and we got, so this is B. I've got 50 volts in a battery. I've got a resistor there of 125 ohms. I've got a resistor down here of 125 ohms. And my equivalent resistor that is sitting there is going to be what? It's going to be, well, 250 minus the 342. So if I go 342 minus 250, 92 ohms. Anyway, so my current total is going to be that 50 volts divided by 342. 342 ohms. So 50 divided by 342 is going to be 146 milliamps. 146 milliamps. Okay, well, that being the case, I want to know the current. The current through the 125 ohm resistor on the top is going to be equal to the current through the 125 ohm resistor on the bottom. Is that what we're supposed to be doing? Yeah, well, on the bottom, which has to equal 146 milliamps. Okay. Now, the issue is, what is the current through the other resistor, which is the R resistor? And I guess what we would do in this case is we would calculate the voltage across the 125 ohm resistor. So I take my current and I multiply it by 125 ohms, and I get 18.27. 18.27 volts. 18.27 volts. And then I ask myself, well, what's the voltage across that equivalent guy? So 50 minus 2 times 18.27, and I end up with 13.46 volts. And then I say, well, wait a minute, I'm done. I don't have to do that. Yeah, I do. Because see, I have currents going this way and coming back that way. I don't have the same current going through the 125 guy. But that is the voltage across the middle 125 guy. So the current through the 125 ohm guy in the middle is going to be that voltage, 13.46 volts, divided by 125 ohms. 108 milliamps. Okay. Looking at number 24 next. And we're supposed to do something. Let's say 24. I have a 2.8K resistor and a 3.7K resistor are connected in parallel. This combination is connected in series with a 1.8K resistor. If each resistor is rated at a half watt maximum, what is the maximum voltage that can be applied across the whole network? Okay, so we have some voltage being applied across the network, and the network looks like that. And this guy's 1.8K. This guy's 2.8K. This guy's 3.7K. And we know that power is I squared R. We know that power is V squared over R. We know that power, that implies that current can be the square root of power divided by resistance, and voltage can be the square root of resistance times power. Okay, so that's just a bunch of equations that we have. And the issue is, what's the max voltage? Okay, so what we're going to do is look at each of the resistors individually to see what the maximum current and voltage could be across each of those resistors. So I look at the current through the 1.8K guy, and so that could be the square root of power, which would be a half watt resistor divided by 1800. So maximum of 0.0167 amps. Well, we wouldn't write it that way, would we? No, I wouldn't. 16.7 milliamps. And then we look at the voltage across the 1.8K resistor that would be allowed, that would be a maximum voltage. And that would be the square root of the resistance times the power. And that would be 30 volts. And then we'd ask, what is the maximum current across the 2.8K guy? And we do the same calculation again, square root of 1/2 watt divided by 2800, and we would come up with 13.4 milliamps. And the voltage max across the 2.8K guy, square root of 2800 ohms times 1/2 watt, and that'd be 43 volts. And then we go and look at the current through the 3.7 ohm resistor max, square root of 1/2 watt divided by 3700 ohms, and we'd end up with 11.6 milliamps. And then the voltage doesn't look much like a voltage, does it? The voltage across the 3.7K ohm resistor I'm looking to make sure that that resistance value is right in the book, is equal to square root of 3,700 times 1/2. And that would be what would that be? 3,700 square root, 3,700 times 0.5, 43 volts. Both of these can't be 43 volts. One of them has to be wrong. So I'm going to look at square root 2800 times 0.5. That's 37 volts. 37 volts. Okay. So now I know the maximum values of those things. And now the issue is, how are we going to figure out which one is going to be, who's going to maximize out our voltage? That's the issue. So it looks like if I have 16.7 milliamps flowing through the first resistor, then that could that's not equal to these two added together. So I've got 22, 23, 25. I have 25 milliamps that could be flowing through the other two. So it looks like that's my limiting resistance. Okay, my limiting factor for current flow. And what does the problem want to know? What is the maximum value that can be applied across the whole network? Okay, so that being the case, I know that I have some voltage max, and I know that this guy has 30 volts across him, and that's the max he can be. And he is 1.8K. And then I've got these two resistors sitting there, and one is 2.8K and the other one's 3.7K. And we know the maximum current is flowing at that time through the smallest resistor, 16.7. Okay, so I've got 16.7 milliamps flowing through that resistor. All right, now if I knew this equivalent resistance of the parallel circuit, then I could figure out the voltage. All right, so I want to know what is 1 over 2.8K plus 1 over 3.7K. And that's going to be the resistance of the parallel network. Okay. 1 divided by 2.8 plus 1 divided by 3.7. Put enough parentheses in, and I'm going to have 1.5938 K ohms. I'm going to send my current through that resistance to find the voltage. So the voltage across the parallel path is going to be 1.5938 kilo ohms times the current I have, which is 16.7 milliamps. Okay, times 16.7. So I've got 26.6 volts. All right, so voltage total has to be the voltage across the 1.8 guy plus the voltage across the parallel path. 30 plus 26.6 volts. So 56.6 volts. And then I'd say, well, you know, I really only have two significant digits in the problem. So my final answer for voltage total max, the maximum voltage allowed, is going to be 57 volts. Now, that answers the question from a physical point of view. It doesn't answer the question from an engineering point of view, because each of these resistors are plus or minus 10% resistors, or plus or minus 5% resistors, or plus or minus 1% resistors. Are not exactly 125 ohms, and the design margin is built in of a 20% design margin is built into those. So if we were to take all those factors into account, if we were given any information at all as to what the percentage was, then we'd have to do all those over again, looking at, well, what if these guys were at the top of their percent tolerance or the bottom of their percent tolerance, and we'd have to come up with multiple answers. But luckily this is not a engineering class, it's only a physics class, so we can deal with resistors that are perfect. Okay, we're looking at number 26. No, we're not. 28. Looking at number 28. Determine the terminal voltage of each battery in the picture below. Okay. So I've got some battery. It has a resistance, internal resistance of 2 ohms. And the battery has 18 volts on it. And we have another battery, and it has an internal resistance of 1 ohm. And it's a 12-volt battery. And they're connected in such a way that so my battery goes from where my dots are, and then I'm connected into a resistor that is 6.6 ohms. And we want to determine the terminal voltage on for each battery. Okay, well, I look at that and say, well, what's my total resistance? Resistance total. 1 ohm plus 2 ohms plus 6.6 ohms. So I have 9.6 ohms total resistance. What's my total current? My total current, 9.6 ohms divided by the voltage. Now, the voltage goes up and the voltage goes down. So if I were to draw my loop in that direction, I would go down 12, I would go up 18, so the voltage I have is 6 volts. 6 volts. And how did I get the resistance on the top and the voltage on the bottom? Who's paying attention out there anyway? All right, we'll try that again. V is equal to IR, so we have to put the voltage on the top, 6 volts divided by 9.6 ohms. Okay, that being the case, then I've got a total current of 0.625 amps flowing. Okay, the voltage drop across my 1 ohm internal resistor is going to be 1 ohm times the current, and we'll call it 625 millivolts. And the voltage across the 2 ohm internal resistor is going to be 2 ohms, 625 milliamps, 1.25 volts. Okay, that being the case, the terminal voltage across the terminal of the top battery is going to be 18 minus 1.25. Oh, yeah. 16.75 volts, and the voltage of the bottom, terminal voltage of the bottom battery is going to be look at our picture there for a moment. And consider for a moment that we're going that way. So my voltage is going this way. I do a drop, and then I do another drop. So in the case of this way, I do a drop and I raise. So it'd be I'd have to subtract the 1.25 from the 18. But when I go the other way, I see a drop and a drop because the current's going the wrong way. The terminal voltage across that guy is going to add. So that's going to be 12 plus 1.25. So I'm going to see a 13.25 volt across the other guy. And then we'd say, well, you know, I really don't have that many significant digits. We'll go with 17 volts on the top guy and 13 volts on the bottom guy for our final answer. But the issue is that the 18 volt battery has the current going a different way. One could make an argument that this would be negative voltage on the battery, I suppose. But other than that, we're done with that guy. Number 32. Calculate the currents in each resistor of figure 26-5. The currents. So we want to go, okay, so what we need is a better than normal drawing so that when we calculate something, we can actually get something. Okay, so 120 ohms, 82 ohms, 64 ohms, a battery, 58 volts, 25 ohms. I think I need a bigger whiteboard. 3 volts, 110 ohms. Well, there's several ways we could do this problem. The first way would be superposition, which means we would do the we would calculate the values twice, and I think that would be the best way to do it. The other way would be get multiple equations, multiple unknowns, and hope that we only have 3 of them. But we could do that too, I suppose. Okay. So why don't we go, it looks like before the way I did it was superposition. So this time we'll do it differently. And we'll do it with multiple equations, multiple unknowns. Okay, so what do we know? We know that we have some current 1 that's flowing that way. Okay, so that current 1 is flowing like that. We know we have some current 2 that's flowing this way. And we know that we have some current flowing that way, and we'll call that current 3. Okay, and so if we look at this node, we see that current 1 minus current 2 minus current 3 has to be 0, because we have 2 currents going in and 1 current going out. Okay, now we're going to go and take a loop that goes around like that. That's what we're going to do. And we're going to say that 58 volts has to equal 120I1 plus 82I1 plus 64I3. Okay, and then we're going to take another loop, and going to take a loop that way, and we're going to, well, we'll just leave it like that for a moment. And what color do we want? We'll use black. Okay, and we're gonna start there, and we're gonna say that the 3 has to equal 25I2. We're going a different direction than the current, minus 64I3, and then we're going to have a plus 110I2. Okay, so there's our 3 equations and our 3 unknowns. So we'll write them down as I1 minus I2 minus I3 is equal to 0, as 202 I1 plus 64 I3 is equal to 58, and as 135 I2 minus 64 I3 is equal to 3. Okay, well, we could do many things with 3 equations, 3 unknowns. My preference would be to use my TI-86 Pro calculator and solve simultaneous equations. So I'm going to put a 1 in and a minus 1 in, another minus 1 in, call it 0, and then 2, 0, 2, a 0, a 64, 58, and a 0, 135, minus 64, 3. And just tell it to solve for the 3 equations, 3 unknowns. When I do that, I get an I1 of 240 milliamps. I get an I2 of 92 milliamps, and I get an I3 of 148. 148, we'll call it 150. 150 milliamps. Okay, was that what we're supposed to have done? What we were supposed to have done? Determine, no, that's the wrong one. Okay, calculate the currents through each resistor. Okay, so now I know the current through, now I got to write down the answer. Okay, so the current through the 120 ohm resistor is 240 milliamps. The current through the 82 ohm resistor is 240 milliamps. The current through the 64 ohm resistor is I3, which is 150 milliamps. The current through the 25 ohm resistor is equal to the current through the 110 ohm resistor, which is I2, 92 milliamps. Oh, do I like those answers? Yeah, I like those answers, but they are rounded out a little bit. Okay, so I'm done. And I did that in less work than I did when I did the problem last time. Okay. Next problem we're going to do is number 36. Determine the currents I1, I2, and I3. Assume the internal resistance of each battery is 1 ohm. What is the terminal voltage of the 6-volt battery? Okay, so that's what we're going to do. And now it's just a matter of, can I draw the picture and be okay. Okay, so this is 22 ohms. I have 1 ohm. 12 volts. 12 ohms. 12 volts. 1 ohm. 11 ohms. 18 ohms. 15 ohms. 6 volts. 1 ohm. And I know that current 1 is going that way, and I know that current 2 is going this way. I don't know that it is, it's just that I'm solving it that way. If I'm randomly choosing the currents, obviously I'm choosing the ones that the instructor wants, that the book wants. Okay. Uh-oh, eraser was too big. Okay, so what we're going to do is we're going to look at this node. We're going to come up with 3 equations to unknowns. So I1 is equal to I2 plus I3. That's going to be our first equation. Our next equation, we will do a loop that way, in that direction, and we see that we go up 12, we go down 12 I2, we go down 12 I1, we go up 12, we go down, that's 12 volts, right? 12 volts, 12 volts. When we go down 23 I1, and that has to equal 0. The sums going around a loop has to be 0. And then we'll look at another loop. We'll look at that loop there, and we go up 6, we go down 19 I3. Okay, we're going to go up because the current's going the other way, and our loop is going that way. It's going to go up 12 I2, then we're going to go down 12, and then we're going to go down 15 I3, and that's going to equal 0. So we're going to rewrite our 3 equations to unknowns. I1 minus I2 minus I3 is 0. And the next equation would be something's equal to 12. So I've got 35 I1 goes on the other side of the equation, making it positive, and plus 12I2 is equal to not 12, but 24. 24. And then the third equation, I'm going to have something equal to 6. So I'm putting the 12 on the other side of the equation and minus 6ing from it. And then what I have on this side would be a plus 12I2 minus 34I3. Okay, so now I've got three equations, three unknowns. In the worksheet in the book, I use Cramer's rule to solve those three equations, three unknowns. We're not going to do that. We're going to use our calculator. So I'll go second function, solve a system of equations. So I've got 1 minus 1, 1. Let's see, 1 minus 1 minus 1 is equal to 0. I already have that. And the second equation would be 35, 12, 0, 24. And the last equation, 0, 12, minus 34, 6. And I find that x1, x, which is I1. Okay, so I1 is equal to 0, well, we'll make it 510. 510 milliamps, rounding off to only two significant digits. And I2 is equal to 510 again, and I3 is equal to 2.6 milliamps. Okay, so I1 is supposed to be I2 plus I3. So we'll go back up and keep that that way. We'll call this 0.07. So we'll round that guy up to 510, but we'll move him down to 0.7, and then that way they seem to add better. Okay. So that looks okay. Looking at I3 again. Yeah, that's what I got. Okay. Now we're looking at the B part of the equation, B, and B wants to know what? What is the terminal voltage of the 6-volt battery? Okay, so the terminal voltage on the 6-volt battery is going to be 6 volts minus the current, which would be the I don't remember. Which current is it? 6-volt battery minus the I3 current times 1 ohm. And the I3 current is next to nothing. And when we do it and we have significant digits, that would be 6 volts. Because we have 6 minus 0.0026 and 6.5, whatever it is, 5.9874, and that would round back up to 6. Okay, so much for number 36. We're going to number 44 next. In the diagram to the right, the total resistance is 15 kiloohms. The battery EMF is 24 volts. If the time constant is measured at 24 microseconds, calculate the total capacitance, the time it takes to get to 16 volts. Okay. All right, so we've got a battery. We've got a battery, and we got a resistor, and we have a capacitor, and we have a switch. Resistor, battery, 15K ohms, and we know the time constant. Time constant is RC, which is also 24.0 microseconds. Okay, well, from the time constant, we can figure out what the capacitance is. So the capacitance is going to be the time constant divided by R, and that's going to give us 1.6 nanofarads. 1.6 nanofarads. 1.6 times 10 to the minus 9th farads. So that's the A part of the answer. Now, we know the voltage across the capacitor is Q over C. And we know the voltage across the resistor is IR. Okay, so now we're to the point of solving the B part of the answer. And we go in the book and we find an equation that says the voltage across the capacitor is going to be the voltage of the battery, 1 minus E to the T over the time constant tau. Okay, so that's going to be the case. We want 16 volts, 44, where's 44? The time and the voltage across the resistor is 16 volts. Okay, so if I have 16 volts across the resistor, that implies the voltage across the capacitor has to be 8 volts. Alright, so 8 volts is equal to 24. 1 minus E to the T divided by tau. That's 1/3. 1/3 is equal to 1 minus ET over tau. That's minus 2/3 minus ET over tau. 2/3 is equal to E to the T over tau. I then take the natural log of both sides. I didn't want to do it when I had a negative number there, that's why I didn't do it earlier. And I have natural log of 2/3 is equal to T over tau. So the time it's going to take to get to the voltage is tau, natural log of 2 over 3. So the natural log of 2 divided by 3 is a negative number. Oh, yeah, there's a minus sign sitting there. There's a minus sign sitting there, a minus sign sitting there, a minus sign sitting up there. And everybody was telling me to put my minus sign in, right? Minus sign sitting up there. Okay, that's perfectly okay. That means I got a minus sign there. That means I got a minus sign here. And I put it in my calculator and I get 9.73 microseconds. And that's going to be the time it takes the resistor to get to 18 volts. Okay, so that's 24. Next we're going to do number 50. Determine the time constant for charging the capacitor in the circuit below. Okay, so I've got some battery with E as my voltage. I've got some resistor 1. I have some resistor 2. And I have a capacitor. Capacitor C. Okay, well, we know the voltage across the capacitor is Q over C. We know that. And what we're going to do is going to say, well, I have some current 1 that's flowing that way, and I have some current 2 that is flowing this way, and I have some current 3 that's flowing that way. Okay, so that being the case, I look at this node, and I see that current 1 is equal to current 2 plus current 3. I see when I do a loop around that way, I see that E is going to equal R1I1 plus R2I2. And when I do a loop around that way, I find that Q over C is going to equal, that's a Q. Q over C is going to equal I2R2. And I take the loop the other way. Oh, that wasn't good. So I'm positive on this side, I'm negative on that side because my current's going that way. I'm going to go that way, and I'm going to have positive Q over C is equal to R2I2. Okay, so those are our 3 equations, 3 unknowns. Now, at this point, we can't put it in our calculator. So now we have to solve the 3 equations, 3 unknowns without putting it in my calculator. All right. So what should we do first? Okay, so we'll call this guy equation 1, call this guy 2, call this guy 3, and I'm going to use 1 to eliminate I1 from the second guy. Okay, so we're going to rewrite it as R1 I2 plus I1 I3 I2 plus I3 plus R2 I2. Okay, so that's what we're going to do. And then we're going to use 3 to eliminate I2 from the guy up above. Okay, and I'm going to get that epsilon E is equal to I2 R1 plus R2 minus I3 R1. Okay, so now I've got these two equations in just I2 and I3. Okay. Now we're going to rewrite them, and we're going to say that 0 is equal to my electromotive force minus Q over R2C, because that's what I2 is, plus R1 plus R2 minus I3 R1. And then we're going to look at I3, and I3 is going to be dQ dt, change in the charge on the capacitor times T, by definition. Okay, so we can rewrite this equation and say I got 0 is equal to the electromotive force Q over R2C R1 plus R2 minus dQ dt R1. Alright, well, now we got a differential equation in Q, so I'm going to go and separate my variables, get Q on one side and dt on the other side. Okay. If I do that, how am I going to do that? So I need a common denominator. So I'm going to have E RC C minus Q R1 plus R2 divided by RCC is equal to dQ dt R1. Okay. then we could rewrite that as dq over q minus R2, that's R2, yeah, that's R2, R2 CE divided by R1 plus R2 is equal to minus R1 plus R2 divided by R1 R2 CT. Okay, so now I got Q on one side of the equation and the T's and the Q's on the other side of the equation. So I'm going to integrate both sides, and on this side of the equation I'm going to have minus R1 plus R2 over R, that's dt, R1 R2 C times T. Okay, and on the other side of the equation, I'm going to have natural log of Q minus R2CE divided by R1 plus R2. Okay. Now I'm going to take both sides of the equation to be powers of E. And I'm going to have Q minus R2CE divided by R1 plus R2 to be equal to E to the minus R1 R2 divided by R1 R2C T. Now someplace I need a constant of integration, so I'm going to have to throw a constant of integration in someplace. And that would probably be a good place to put it, would be there, K. Fine. And then that's out for Q. Q is equal to R2CE divided by R1 plus R2 times 1 minus E to the minus R1 plus R2 divided by R1 R2 C T. Okay, now Q is going to be some initial Q, 1 minus E to the minus T over time constant over T. And so what we're looking for is the time constant. So the time constant is sitting right there in our equation. So the time constant is going to be R1, R2, C over R1 plus R2. Oh, we all love that, I know. Well, that ends the problems I'm doing in chapter 26.